Okay, I have a question in regards to the final.
Uh-huh.
Um, if possible, do you know if there's any specific topic that you've noticed that students typically struggle with that maybe you can recommend that we spend a little bit of extra time reviewing and preparing for?
Yeah, so I mean there are two things that usually like I mean there is a bunch of things where students kind of really, like over time have been making mistakes on, but basically one of the kind of common themes is that essentially they don't pay too much attention to the material before the final. So essentially, I mean, about like maybe 25, 30, 35 points on the final will be from like the stuff that was covered by the midterm. So kind of don't neglect that, because if you totally like bomb that, it's gonna be like a C kind of grade. So essentially, in order to do well, you really need to know at least something there. Uh, Now for I'm not gonna tell you like which parts of that material are gonna be on the test, but basically as you have seen already on the midterm, I try to allocate a lot of points to things that are kind of pretty important, so you can kind of see like what are the overall like basic things that you need to know how to do well, right? So essentially, what I tend to do is basically ask questions that are not some sort of like a totally. I mean, if there is like a totally obscure question or something and so on, then usually it gets like a relatively small point allocation, right? And I try to not make them like totally obscure, as in you really have to have read it. It's more like you can figure it out even if you. I mean, if you understand kind of the overall material, you should be able to figure out, what the answer to the question is, right? So that's kind of one of the things. The other, I mean, one of the things to kind of consider when you're figuring out, what to study. Basically, it's not so much gonna be like stuff that was kind of kind of fine points on the midterm. It's gonna be probably some stuff that I think you really should know even now. And you have seen like how many points were allocated on the midterm to certain things and stuff like that. So basically, that kind of argues for, at least you should know your branch prediction and your, how the ROB based processor works, and how Tomasulo's algorithm work. I mean, stuff that basically is kind of the one of the main topics on the course, in terms of, you really kind of should know how that works. And as you have seen, for like VLIW and stuff like that, the kinds of questions that are asked are basically the kinds of questions that you really just need to know, like, what is VLIW, and kind of why is it done that way, and what are kind of the main differences from the traditional processors and stuff like that. So that essentially, like, when you get questions of that nature, you will be able to answer them, right? So for the material before the midterm, basically there will be, I mean, it's not going to be like most of the final, but it's going to be a large enough chunk that you really cannot afford to like not do that well, right? So pay attention to that, especially like go over your midterm, make sure that the mistakes you've made before, don't apply again. I mean, you won't make them again and stuff like that. So that's one of the things. The other thing is basically that of the kind of post midterm material, essentially. Again, I mean, it's going to be kind of the same types of things, as in it's going to be basically, you either need to, I mean, if there is like a mechanism of some sort, you need to understand it pretty well. If there is a concept of some sort, you need to understand what the concept is, not necessarily like every fine point about it, but basically, like, if you know about kind of the main points of the concept, as in like what is it about, why it was done, why do we do that way, what are the other options, if any, and stuff like that. I try to ask questions that are basically going to be you know kind of answerable in that way. So it's more like trying to test the understanding of the concept than kind of some sort of did you read something or something. So for example, like I will not ask. I mean, I never ask questions like, you know you know on the most recent x86 processors, what's the ROB size or something like that. I mean, a lot of architecture courses actually, like that are out there, and I've seen my fair share of those. are going to essentially have some sort of, we cover the, out of order execution, and then we're going to cover basically like in a lecture or two, in this case, there will be like a video or two about like, what are the modern processors doing in that regard, right? And then the test will be like, kind of, did you remember what we told you modern processors do? Which I mean, like what specific numbers some processor uses is kind of beside the point, as in, that's going to change in the future probably. What's probably not going to change is if there are some sort of a trends or tendencies or reasons for some parameters being in some particular range. So for example, if it's like, what would be the typical issue width of processors that are like, let's say, high performance processors, I mean, it's not going to be one or two simply because that's not going to be a high performance processor, but it's not going to be like 8 or 10 because there is no processor with 8 or 10. And there is a good reason for it, right? So basically, a very simple processor will have a narrow issue with, right? A fancy processor you want to have a wide issue with, but there are limits. I mean, like the, a wide issue with comes at a tremendous cost. So basically, going kind of, I mean, you will have maybe 4, 5, and 6 are kind of feasible. Beyond that, basically, you are like, implementing an issue width of 8 in an out of order processor. I mean, you could make like 2 processors of issue width 4 and just put 2 cores like that, and they're probably gonna, I mean, the 8 issue processor versus 4 issue, it's not going to be a huge performance difference. Remember that, when there are dependencies and when the processor cannot find what to do in a cycle, essentially it kind of, issues less than its issue with, right? So essentially there are these kinds of trends and stuff like that basically, kind of determine, what's reasonable and what's probably going to stay. So some of the numbers kind of slowly creep up as things get better. Some of the numbers kind of surprisingly, kind of have been going up and then kind of stayed in a particular range, and there's a reason for that and stuff like that. So one of the things to kind of pay attention, for example, is if you understand, the concept and what are the trade-offs in it and stuff like that, you should understand it well enough to, for example, when you get a ridiculous, I mean, so this is not like I'm going to ask you what's a reasonable number. It's more like you're going to solve a problem and come up with a number. You should then think about, like, is this a reasonable number? Because I don't give you numbers that like absolutely make no sense. I try to give you numbers that are relatively reasonable, right? And if something totally absolutely makes no sense, you should probably like revisit that as in maybe it's wrong, right? So it's I mean, essentially when you get results, kind of think about like what are the parameters of the problem, what is your solution, does that solution make sense for a problem with those kinds of parameters, right? For example, on the midterm, I mean, not this time, but there were instances where there is like, okay, this is the fraction that is not that is not optimized. Then you have like on the optimized fraction there is like a speed up. Let's say half of the program cannot be optimized. On the rest, you get a speed up of 10. Okay, so the question would be usually like, okay, what's the overall speed up, right? And if you could achieve any speed up on the optimized portion, what would be the maximum achievable speed up theoretically, right? I mean, that was one of the midterm questions, right? So one of the things that cannot happen is that you have basically the actual overall speed up with the given finite speed up on the optimized part be somehow more than the maximum achievable speed up under like infinite speed up on that part, right? But so essentially, things need to make sense basically. Like if you have two answers like that, like you should have noticed something is kind of fishy here, right? Same thing for example, when people go over the ROB based problem and kind of try to come up with numbers. So once you come up with the numbers I mean, on the midterm again, like think about basically doing some sort of do these results make sense, right? So for example, when you have something like when does a particular instruction issue execute and stuff like that, you should kind of just like once you come up with a table like that, you should kind of go back to it and maybe just check, do these make sense just by kind of like a overall bird's eye view of like issue should probably not be happening out of order, commit probably should not be happening out of order, any instruction should kind of have a sequence of issue, execute, broadcast, commit, in which the numbers are kind of going up in that sequence. So you cannot have like, it executes in cycle 3 and it has been issued in cycle 5, obviously, and stuff like that. And but sometimes people just kind of for every number they kind of try to figure out what it is, and then they kind of make a mistake there, and some of these checks would be kind of trivial for finding those kinds of mistakes, but people just don't do. And then again, don't like redo the problem again. It's more like kind of just things that make sense, like some things should be in order. Some, I mean, some things should kind of be like a sequence of numbers that just goes up. Some of them can be different. Some of them are like, okay, the instruction, for example, issues and then waits for a long time and then executes. Well, you should check, is it waiting for something? If there is no dependence in the program, that instruction should be executing pretty much, as soon as it issues, unless, so basically the only reason for an instruction to not execute are either that it is waiting for something, or that the execution unit is busy. And again, if many instructions will kind of execute pretty soon after the issue, so for those, oh fine, I could be off by 1 or something like that, but if you have an instruction that kind of doesn't execute for a long time after it issues, just check if there is a dependence on something. If there is no dependence, like, is the unit busy? If not, then like, why is this not executing, and stuff like that. So basically, some numbers kind of scream like, like this is wrong, or this might be horribly wrong, and you want to kind of just take a look at it, so that and I tend to kind of, I mean, when there are penalties, for mistakes and stuff like that, I tend to penalize more the mistakes that were like, I mean, this cannot be true, as in I don't need to do the problem to tell you that this just cannot happen like this, right? So basically, like something that with basic knowledge of architecture you should have noticed something is like really wrong here. As opposed to something that is basically, the number is a little bit off or something like that. So basically, yes, you didn't do it correctly, but by kind of just knowing architecture in general and kind of glancing at this problem, it wasn't obvious that this is a wrong result, right? So pay attention to basically this kind of like major blunders that are essentially kind of indicating not only that you kind of made a mistake on the problem, but also that, like, if you glanced at these numbers and you knew any architecture stuff, you should have known that this is horribly wrong, right? For the stuff after the midterm, basically, what you probably need to pay attention to is, I mean, as you have seen, like, there was a lot of stuff about coherence and how it works and directories and stuff like that. That tends to imply that basically there will be kind of a whole bunch of points allocated for some coherence related things. So pay attention to like how coherence works, what are the states, which state means what happens when you read or write and stuff like that. Pay attention to, I mean, for consistency stuff, basically pay attention to kind of, I mean, the overall concept of consistency is essentially that when we write a value to memory, the memory should somehow behave in a way that makes sense to programmers, right? So essentially, consistency is about basically, I mean, coherence is about basically just you write a value and others should then be able to just read it and use it, right? So coherence is easy from the perspective of conceptually what is it supposed to do. Implementation in practice is relatively complicated, right? Consistency is more about if I write to two variables, and I rely on that order, I mean, on the order of writes, or if I read a variable, then write to another one, and again, like, there is something that depends on that order happening in that way, then basically, there is stuff that we need to do to actually make sure that sort of a thing happens, right? Because unfortunately for coherence, if we serialize everything, then I mean, if essentially we have a bus, basically, as you have seen, coherence becomes easier that way, right? But what consistency has as a separate problem that coherence doesn't have is essentially that the processor is allowed to reorder things that it thinks are independent of each other. So basically, when I do two reads from memory, as far as the first one being a miss and the second one being a hit, so the second one really happens sooner because I get a value in a register sooner than the other one. If we have a single core processor, that cannot never be a problem, because there is if I'm reading the two values basically at the points if there is no writes in between in my thread, essentially, then the two values, regardless of in which order I read them, basically like you read A or read B or you switch the order, doesn't matter, right? But when you have a multi-core processor, it does matter. Because and in the videos we have seen examples of like why does it matter and stuff like that, and it has to do with basically if essentially consistency is more about kind of having maintaining some sort of a causal order of things, right? Like for example, if I test a flag and then read a value that is allowed, and then do a read that is allowed by the value of the flag, then essentially, it does matter in which order I did this, simply because if somebody writes and they treat this also as like, oh, my order of writes doesn't really matter because I'm writing two values, I can write A and then B or B and then A. But if it's a put something in a variable, then set a flag that enables a read from it, then, well, it does matter, right? So essentially the architecture, the machinery of the processor doesn't really understand, when the order matters and when it doesn't, right? And that's why we have all these consistency models, basically starting with the sequential consistency model, which basically says, you need to make sure that everything appears as if it was done in program order, even as far as the memory reads and writes from this thread are concerned. And the idea is that basically, if that's true, then essentially all of these things that where the order matter will be handled in a way that is correct, simply because we treat everything as if the order matters, right? And then you go all the way to really relaxed consistency models, where basically the idea is that any ordering is allowed unless the programmer explicitly specifies so, and what do we ask the programmer to specify becomes increasingly to the point, let's say, as you relax the consistency model. So essentially, in the sequential consistency model, the programmer doesn't have to specify anything, right? And then you have program orderings that are basically like the weak model, and so on, and eventually you come to like these lazy release and other programming consistency models, where basically like there is no ordering maintained among your reads and writes to different variables, unless you specifically say that like this read should happen before this write in my program. And you kind of need to specify that, basically, that essentially, like I've written A, I want you to make A's write visible before you read B here, right? So and the idea is basically that of course allows the processor to do most of the reorderings it would be able to do without consistency, while allowing programmers to still write correct programs. But the problem is that, of course, the programmer now really needs to understand where the order might or might not matter, right? And so on. So for consistency, basically, the kinds of questions that I tend to ask are either I don't ask you like, in the release consistency model, kind of add fences and stuff or add releases and acquires in order to make this correct or something like that. If I ask you to do that, it's going to be something like really simple, like something where it's kind of obvious what you should be doing. But I can ask like kind of more like conceptual questions, like which kind of, if we do this, what are the possible orderings that might happen in a like for example, which order of events here is possible with the sequential consistency, for example. I'm not going to ask you to understand like the nuances of every single consistency model, but you should understand the nuances of the sequential consistency model, because it's really trivial, as in it's kind of the strictest of the models, and the one where basically everything that the programmer does behaves the way we humans tend to expect sequential programs to behave, right? So you should know what should happen under the sequential consistency model. Now the interesting things are that under the sequential consistency model, now you would think, okay, that means that basically only one order of things is allowed, but that's not true. So basically, if you have multiple threads, the access is from, kind of one thread does this sequentially, the other does this sequentially. They can still happen kind of in multiple, interleaving. So basically, it's not like, thread one reads A, thread B reads B, and so on, and then we can, kind of just say they have to be done kind of in a round robin fashion or something like that. No, I mean, if we have, let's say, read A, B, C, and D in one thread and write, X, Y, and Z in the other thread, it can be that A, B, C, D are read first, then X, Y, and Z are written, or it could be that they're interleaved. So there is like A and then read X and then B. But not all orderings are allowed. So for example, there can be no ordering in which somehow B is read before A if this is a sequential consistency model. So you need to understand. I mean, you need to know these things basically. That kind of coherence still. I mean, the normal dependence checking in the processor and coherence and stuff like that are gonna essentially enforce the ordering of accesses to the same variable. So basically, even in the most relaxed consistency model, if I write to X and you read X, you're gonna, and you read X kind of after what I wrote, you should be reading X that I wrote. Why? Because this has nothing to do with consistency. This has to do with coherence. Essentially, when I write X, it's gonna invalidate all the other copies. When somebody else reads X, they're gonna have to get my copy because that's the only copy that is left. So understanding kind of the difference between consistency and coherence, just in terms of basically what one allows and what the other allows is pretty essential. So pay attention to those kinds of things. Now for example, the caches and the memories and stuff like that. For caches, what's important is to know like how does it work, and the blocks and the indexing schemes, and I mean just how does the sets and ways and stuff like that work. For memories, basically you should really know like kind of what happens in a memory kind of array, basically once we give it an address, essentially. So like what's the kind of I mean like there is a row decoder, there is a cell array. Why do we have the row decoder and the cell array and stuff like that? As in, why don't we just have basically a bunch of flip-flops? Why do we why is DRAM memory volatile? As in, why does it lose content if it's not powered? And why do we want that? As in, like, why not build a memory that is more like register-like, so it just keeps the state and we don't have to refresh it? What's a refresh? And stuff like that. So essentially, there are some concepts that if you look at the lessons, basically, there are some things that are like, okay, this is a thing that is kind of not really like repeated over and over, but like, we kind of teach you that, and then it ends up being used for a lot of other things, right? And you really need to know those things, right? Things that are somehow like we introduce a concept and we never really use it. It's like, okay, you should know what the concept is. You might lose a couple of points if there is a question about it, but I'm not gonna make like a 20-point question on that. Right, because there is a chance that somebody just doesn't know that one thing and loses 20 points simply because they don't know how to begin the problem, right? So I tend to kind of when I give problems that are worth like a lot of points, they tend to be about things that basically a lot of time is spent on them, and kind of like the ROB thing. So it's probably going to be like a kind of coherence based thing like that, and stuff like that. So pay attention to this kind of like really basic. You really need to kind of, there's a mechanism that essentially ensures something. You need to know how that mechanism works and why does it ensure what it's intended to ensure, as in which parts of the mechanism kind of serve which purpose for like there's a reason for why we need this, and then the mechanism basic. I mean usually, like for example, the instruction scheduling, it's a mechanism that essentially does multiple things at the same time, but the overall goal is basically to be able to kind of run instructions well, I mean, kind of keep the processor busy, basically, while still maintaining the illusion what the programmer said should be done. Well, coherence kind of has the same thing, right? Like it's supposed to allow us to do caching locally while maintaining the illusion that we're not doing that as far as the programmer is concerned. So essentially, you know, which parts of which states and so on allow you to do which kinds of things in the cache and stuff like that is reasonably important. So basically, you need to understand like for all of the the MOSI states, you need to know like what do they do, and why we have it. Like if you are forced to remove one of these states from the MOSI protocol. I mean, MESI we already kind of have examples of that in the lessons, but you could think like what if I couldn't have a exclusive state? What if I just have the ownership and the shared and the M state and the I state, right? So it would be like MOSI, okay? What would happen then? I mean, some of the protocols are just like not really feasible. Like for example, if you have SI, that would be really tough because you couldn't write to your cache, but it's possible. It's possible. I mean, what that would do is essentially you would not be able to write to your cache. What you would have to do is invalidate all of the cached copies and write directly to memory every time you do a write, right? I mean, every state basically. I mean, if you only have the I state, that's basically you don't have a cache, right? So in a sense, every possible subset of states is theoretically doable. It's just that does it really make sense? As in, why would you do that? Because you would still have to implement something, and that something will probably perform poorly. So essentially, the reason why people pick like particular state, like there is kind of the protocols that you have are basically MSI, MESI, or MOSI, and the reason is that essentially, each kind of state that we add to that sequence basically is slightly less valuable than the ones we already have, right? Because if you look at like why do we need the E state? Well, the E state is needed to essentially allow us to read something and then write it without invalidating anybody else. That's slightly less valuable than being able to cache things that we keep writing to and being able to share read-only data, of which there is a lot, right? Because so essentially the exclusive state kind of serves this purpose of basically, if I'm the one who reads and then writes something, I should, and nobody else really wants it, I should be able to do that. But it basically optimizes for only that first access when I read it and then write it. After that, if it's still in my cache, it's gonna be in the modified state anyway. So basically, if I didn't have exclusive state, what would happen is I would bring it in shared first and then modify it, and after that it's gonna be in the same state that it would have been with MESI. So basically MESI just serves to kind of this first load gets optimized, as opposed to the shared state, which basically for read-only data, if we didn't have that, we would be in deep trouble, because we would have to keep invalidating things just so that I have the only copy of the data that I want to write, and everybody else will be doing the same thing. So basically, read-only data that everybody reads would forever be ping-ponged around the system. So obviously you want to have the state first, right? So understanding this, what do the states do? I mean, like for each state, like why do we want to have it? What does it do? What kind of a problem does it solve? And how does it behave? Is pretty essential. So you really want to know that. Okay, and I mean, other than just kind of not having studied some major part of the class, or paying too much attention to kind of the really detailed facts, as opposed to basically trying to understand the overall like what's going on here. I I mean, I haven't seen any like really systematic problems that I can describe without describing like the specific question that would be asked, and then like this is why the students answer this wrong, and what kind of I mean, most of the problems basically stem from essentially people focusing on like the details without like kind of seeing the forest for the trees, essentially. And again, there are two aspects of this. One is basically focus on understanding rather than just memorizing stuff. The other one is basically focus on essentially when you're done with the problem, kind of glance at it with the eye towards, does this make sense? And if you did study and you know what makes sense, most of the really bad mistakes, you would at least notice you made them. You may not know what the solution is by just looking at but it's like, okay, this seems horribly wrong. Let me take a look at what's going on here. Okay.
Thank you. Um, okay, I think
Now
a
it's
couple.
it's going to be a 3-hour exam. I'm gonna make an announcement a little bit later, maybe in like 3 or 4 days, because I noticed if I make the announcement now, basically, then people will kind of glance at it, forget by the time the final comes. So I try to make the announcement about like maybe 3 or 4 days before the final, so when people are in the final, final exam, pay attention to mode. But essentially, it's going to be a 3-hour exam. It's going to maybe have like one more question than the midterm had. So it's not going to be like too much longer. But because there will be more diversity of topics, I felt I should give you more time, because basically you kind of will need to do some problems that had to do with the midterm material, and then still, do separate things that basically have to do with what was taught after the midterm. So I figured the questions are going to be a little bit more diverse in terms of when something was taught, and how many lessons do you do. Essentially, the kind of the context switching cost between, like we're talking about caches here, ROBs here, and stuff like that, usually implies that students need a little bit more time to just kind of be able to kind of put themselves in a frame of mind for solving a particular problem. So you'll have more time mainly for that. There will be maybe like 10-15 minutes more needed to actually do the exam than for the midterm. So it should be a little bit less kind of time pressured exam than the midterm was.
Well, that's good to know. Thank you.
Yeah, no problem. Yeah. And
So
it's essentially going to be like the same kind of structure. I mean, basically, the rules will not change from the midterm. So essentially, it's going to be, proctor track, canvas, same things allowed and not allowed, and stuff like that. I mean, the only major difference is basically just like what's going to be covered, you know, how much time you have, and kind of the kind of maybe one more question. Yeah.
okay, I have at least two questions about the
Uh-huh.
cache coherency protocols, the
Okay.
MESI, MOSI, MOSI.
Sure.
Um, so the first one, really quick, with the MOSI and MOSI protocols,
Mm-hmm.
just to double check, when a cache is in the M state and it switches to O, a write
Mm-hmm.
back does not occur, correct? To memory.
Yes. Yeah. So I mean the write back. So basically the O state really does two things, right? One is that you don't have to do the write back at that point. So basically you can supply the data to. I mean there are two things, right? One is you are allowed to supply data to other caches even after you lose the write capability, right? Because in the M state, essentially, you downgrade to S when somebody reads. And now, because everybody is in the S state, nobody really can supply the data on the bus, because all they know is that I'm in the S state. If in that state I do supply the data on the bus, then the problem is that everybody else who is in the S state, and obviously there could be more, will try to do the same thing. So there will be a conflict, and so on. So mostly, I mean, the O state basically fixes that problem, as in, I essentially, I mean, as far as sharing is concerned and who can write, I'm one of the read sharers. I cannot write. But as far as who gets to answer to queries, I am the one who gets to answer, because of that could be only one that is in the O state, right? So O allows you to do that. It allows you to basically do interventions, even when there are other sharers. It also allows you to, because again, who's gonna write back is the problem for shared. You don't want, if I'm in the shared state and I want to dump the block, I need to write it back. That would be bad, because there could be a lot of sharers. The memory would see a lot of write backs that are totally unnecessary, because everybody would be writing the same copy, right? But in the O state, essentially, you now know that basically I've fed this block to others, but somehow I'm still kind of responsible for feeding its value to everybody. So that means that memory will never need to respond as long as I own this. And that also means that if I don't want to write back to memory, I can delay the write back as long as I have the block in the O state. So basically, now essentially, if you have the block in the M state or the O state, you don't have to write back until you downgrade from out of those two states, right? One of the neat things about the M and O is essentially if there is one writer and multiple readers, what can happen is basically I write, get it in M, others read it, I downgrade to O, then I write it again, and I invalidate them, promote myself to M, but I never have to do a write back. So basically, we could be going on for a long time without ever writing a write back, as long as we are maintaining as long as basically whoever is writing doesn't actually need to dump it out of the cache.
Okay, that's cool. And then also under this protocol, whenever a new cache or a new core, sorry, requests the data, it never has to read from memory. It can always get it from the core, which has it either in the O state or M state.
Yeah. I mean, and the idea, and also note that like if I write something and then you read it, now I maintain the ownership, right? If you now want to write it, you invalidate my copy, right? And get into the M state, and then you become responsible for writing it back. So basically, if you have a pattern where I write something, then you read it and write it, and then somebody else reads it and writes it, the kind of the ownership of this block kind of goes through the system, right? But again, you don't have to write back. So essentially, the O state is intended to pretty much do these two kinds of things, right? One is to allow me to supply others with data. The other is to not have to write back to memory. Now, when you have a directory-based protocol, then the value of this I can feed others with data kind of goes away, mostly. And the reason is that when there are sharers, the directory knows who the sharers are. And the directory also knows, which of the sharers, are. I mean, basically, the directory knows when there is really like, 10 sharers. It knows exactly who they are. And what can be done with the directory protocol is basically, let's say that we are all in the S state. There is no O state, right? When another sharer requests the block, the request goes to the directory. The directory basically has two options. One is totally allowing, one of the options is basically read it from the slice of the L2 cache that is local to the directory. That means it doesn't need to ask anybody to do anything, right? It just can locally source this from the slice of the last level cache and supply the data. And that's usually more efficient than going, kind of sending a message to, let's say, the owner, who, first of all, the directory would need to know who is in the O state. Second, it would have to forward the request to them so that they can respond. And basically, this kind of going to that owner, sending a separate message from the directory to the owner might take more time than actually reading it from the slice of the level 2 cache. The level 2 cache takes some number of cycles. The last level cache takes some cycles to get the data. But the message traveling around the chip also takes some time. So basically, you lose a lot of the value of basically being able to feed others with data, just because the directory can kind of do that anyway. Second, even if you don't want to read the last level cache, let's say it's really slow, it's still faster to send a message to somebody else. The directory can just pick one of the sharers, any one of the sharers, and ask them to do that. So the directory doesn't need to, we don't have to kind of have a designated owner. What the directory can do is basically it can essentially pick who, if it's really smart, it can even pick like whoever is on the way. As in, I know who is asking for the data. I know who has the data. I'll pick somebody who is kind of halfway between me and the requester so that I can send the message to that sharer, and then they respond, and that basically message flies almost the same route that my data, if I sent it, would have flown, right? So essentially, the value of the old state in terms of kind of preventing basically the memory from responding suddenly kind of diminishes when you have this, because essentially the directory can do most of what the old state can do, and oftentimes it doesn't even want to do that, right? The write back issue is also kind of diminished, because basically when I have the coherent caches, usually there is a shared last level cache on the chip. And when that's the case, basically the write back no longer goes to memory, it goes to the shared cache, and it can handle the writes. So I mean, it can handle much more writes than memory. So basically, typically when you have the directory, you either don't use those state, or if you use it, you only use it for this kind of write back, issue, as in you use it basically to just avoid traffic, or the write traffic to the large last level cache. Typically, that's more important for the sake of energy consumption than for the sake of it cannot handle the bandwidth. As in any write, I mean, any access to the last level cache is typically much more power hungry than accesses to the local caches. So essentially, I might want to prevent writes to the last level cache simply because they're power hungry, and I want to maybe maintain this, kind of, like write backs only happen when the ownership is low. I mean, when nobody owns or has, I mean, nobody's in the M or O state anymore. So for example, if there is a question about what does the O state do, and it typically, the question will be is the one of the person, kind of, does O state improve this? Okay, that it actually improves two of the things, right? And you want to know at least one of them, but it's better to know that there are really these kind of two main things that it's trying to solve, and that kind of one of them is much more important on the bus. The other one, it kind of diminishes in importance when you have a directory, but it may still come in handy depending on the parameters of the system.
I'm guessing it's also in the case of the directories important
Mhm.
when you don't have the inclusion property, and so a block exists in a different core's level 1 cache, but not in the last level cache. So in that case, the directory has to forward it from
Yeah,
the foreign core.
yeah. If you're trying to maintain, exclusion, or if you don't maintain, I mean, so it's kind of interesting. So basically, when you don't maintain inclusion, what you get is almost everything still has inclusion. So basically, not maintaining inclusion simply, like inclusion is this thing where basically if I remove it from the lower level cache, from the last level cache, let's say, I have to remove it from all the other caches that are sitting between the core and that cache, right? So inclusion is more like every block that is in a level 1 cache has to be in level 2 and level 3, right? Then there is exclusion, which means if a block is in level 1, then it's not in level 2. So basically, you're kind of enforcing them not being in both caches, so nothing is ever in both caches at the same time. And then you have this kind of thing that is like neither inclusion nor exclusion, which is basically just let things happen. And what that does is basically it mostly behaves like inclusion, but periodically breaks inclusion. As in, things by themselves will maintain inclusion most of the time, but it is not strictly enforced, as in there will be things that are replaced from level 2 cache, for example, that end up still being in the L1 cache. But just because the L2 cache and each level of cache is kind of, the, L3 is typically much larger than L2s. L2s are typically much larger than L1s. And that means that a block that is important enough to be in an L1, as in it's one of the 5 most recently used blocks, it's probably also going to be one of the 1,000 most recently used blocks too, right? So essentially, because we have this, the cache is trying to keep recently accessed stuff, and the cache keeps, whatever its capacity, the most recently used 4 kilobytes or most recently used megabyte, or so basically, a larger cache will tend to keep the same stuff that a smaller cache would have plus more stuff, right? the reason why inclusion gets broken sometimes is that a cache typically counts what's recently accessed based on the request it's getting. So essentially, if a block is used all the time, so much that it's never replaced from a level 1 cache, then the next level cache doesn't see any request for this block, right? Because all of the requests are satisfied from the level 1 cache. So the L2 cache might decide that this is the least recently block eventually in its set and replace it, right? Which if you're not maintaining inclusion, is actually okay. I mean, it's actually kind of closer to the optimal behavior for this cache as far as keeping stuff that it actually is asked to provide, right? If you're maintaining inclusion, this sort of a thing can actually cost you because like maintaining inclusion in this case costs you performance, because when the level 2 cache decides to replace this block because it's not used at all in the level 2 cache, it is forced to also invalidate it from level 1 caches. So occasionally the blocks that you're using all the time kind of go away on you simply because the level 2 cache decides that nobody's using this, right? So essentially, inclusion is not maintained for performance reasons. Inclusion is maintained for simplicity reasons. You maintain inclusion to make some other things simpler. Because if I can assume that whatever I, let's say, replace from level 1 is always going to be written back to level 2 because it has to be there, then I don't have to worry about basically me replacing something from L1 and having a miss when trying to write it back to level 2. So you don't have that. For coherence, you don't have a problem of essentially if every core has a local level 1 and level 2, and I snoop in level 2 in order to decide whether I have it or not. If I have inclusion, I just need to snoop in L2. If it's not there, then I don't have it. If, however, there is no inclusion, as in I'm not maintaining strict inclusion, then essentially it might be in my level 1, even though it's not in my level 2. So snoops need to be done on both caches, which again, it's kind of like it complicates things basically. Now my level 1 cache essentially has to have the ability to service snoops and stuff like that, which normally it didn't. So that's the reason for inclusion is always something else. The reason for exclusion is if you do have caches that are that are kind of not of negligible capacity relative to the others, as in, let's say my level 3 cache is not that much larger than my level 2 caches, so that having kind of the overall joint capacity of the two caches as my kind of virtual cache would actually be valuable. Then you kind of say, oh, I'm going to do exclusion, because if I didn't explicitly do exclusion, most of the stuff would have inclusions, which means there would be replication. I mean, like most of the stuff in my level 3 will be also in level 2, so essentially I don't really get the effective capacity of the L2, right? So exclusion is enforced not to, again, like the reason for exclusion is basically if I want to achieve kind of the effective capacity of the cache is larger, is the sum of them, not the kind of the largest one of them. So typically what you have is you typically try to do exclusion basically when essentially your last level cache is not that much larger than the sum of the other caches. If it is, then you're going to complicate things and stuff like that just for the sake of exclusion, right? Because again, exclusion takes work. You have to actively maintain it. The inclusion, strict inclusion, is kind of it needs a mechanism to maintain it, as in you need to strictly check for it, but it's something that you don't really have to enforce that often, because things are inclusive anyway by default. Exclusion is much more work to maintain, and the reason you do it is basically just that, like okay, then essentially if I have like 2 megabytes of L3 cache and 1 megabyte of L2 cache, and I make them exclusive of each other, then essentially I kind of can keep 3 megabytes worth of data on my chip.
I have another question here on
Mhm.
caches. local hits and misses versus global. It seems to me the distinction between local and global only applies for non-level one caches, and that if we're
Yeah.
talking about level one, okay, just wanted to check if that
Yeah,
was
yeah,
correct.
yeah. But basically, local is like of all the accesses, this cache observes what is the miss rate or the hit rate, right? Global is basically of all the requests that the processor makes, what's the miss rate or the hit rate, and basically level one cache sees all the requests by the processor, so essentially its local and global miss rate are the same. For all the other caches in the hierarchy, though, the distinction is pretty important. And the reason for kind of this distinction is basically, like, why do we have both? Why don't we just pick one and call it the miss rate? Is that essentially the local miss rate is kind of what we, for example, like the local miss rate is what you normally would use in the kind of what's the average access time for the process requests, right? Like of all things that miss in L1, how many hit in L2, right? The local miss rate, though, when we're kind of comparing, is it worth having this cache, or what's the kind of overall kind of what's, how much memory is this cache able to handle? The global miss rate is slightly more representative of what you want. So for example, you can say like, oh, a system with a level one cache of, like, let's say 4 kilobytes, my 4 kilobyte level one cache has an awesome 90% hit rate, right? I put a level two beneath it, and that one is like a megabyte size cache, and that one has only 70% hit rate. Okay, so somehow, like, if you look at the local hit rate for a cache that is kind of somewhere below, low, kind of closer to memory in the hierarchy, its local hit rate is not representative of how good of a cache it is, as in, how much it is contributing, let's say, to the overall system. Because basically, if you kind of, if you remove the 4 kilobyte cache and let requests go to the 1 megabyte cache, suddenly its hit rate would be, totally awesome, and being like 97%, because essentially it's handling, you know 70% of the 10% that are missing over there. So basically together they have 97%. So basically, if you look at like the global hit rate of 97%, it's kind of telling you what this cache is kind of helping achieve, right? And also, if you compare the global hit rate with and without this cache, it would be 90% with only the level one versus 97%. It kind of tells you how much this cache is contributing to the overall hit rate, as seen by the processor, and like as seen by not going to memory, right? So the two kind of are just easier easier to make sense out of the kind of the behavior of the cache when you look at like one or the other, depending on the context. But yeah, level one, essentially the two are the same, which is why the concept only becomes relevant when you have multiple levels of caches. As long as you have a single level of cache, pretty much it's just the miss rate.
Okay, thank you.
Yeah.
I think that's all the questions I have for today, to be
Okay.
honest.
Well, no problem. There's still nobody here, which I'm kind of hoping that next week maybe, because if you, like, just a kind of for those of you who will listen. I know that the final exam will be like not this weekend, the weekend after, but so we're getting pretty close to it. So it's time to study, if for everybody who needs to, and the next office hours, I will be in a very different time zone, so I have to figure out what my schedule will be when I get there. I might need to move so I'll try to keep them on the same day, just maybe move them a little bit earlier or later, and I'll try to make kind of to have it make sense for most of the world. But you know it might actually like be essentially kind of evening in Europe, which would be kind of noonish in United States. Or I'll try to maybe do it like early morning in Europe, which would be like really late at night in the United States. I'll be in Germany, so that's that's kind of 6 hours ahead of Atlanta, which is like 3 hours ahead of California already. So essentially, we're gonna, depending on where you are in the US, it's gonna be like 9 to 6 hours difference. So try to find something that I can do, as in I'm not in a meeting there, while kind of not being at 3 a.m. for most of the United States, and hopefully for like everybody like in Asia and stuff like that. Yeah, oftentimes when we kind of need to find something that kind of works well for most of the world, people in Hawaii, suffer because
Well, to be honest, Professor, this is my 8th class so far in the program, and it's the first time I've been able to attend office hours live. So I'm really thankful for
okay.
the time you hold them.
Yeah.
Thank you.
Okay. So yeah. I mean, unfortunately, no matter when we put office hours, there will be some students for whom it's like horrible as far as like when, and part of the problem is the time zones. Part of the problem is just like what local time would be horrible, because for some people it's like midnight is horrible, because if they have kids, wanna sleep at midnight, because kids wake up early. And then for some people it's like noon is horrible because it's in the, or like 10 a.m. is horrible because they have to be at work then and they cannot do this. So essentially, what's a good time changes both with time zone and with like exactly what lifestyle the person is trying to maintain, and what schedule you have. And that means that like no matter how well we pick the office hour times, somebody will suffer. So I kind of try to make the time such that it kind of has a reasonable chance of working for most time zones, as in you can physically make it, and it's not like 3 a.m. all the time for most people. But depending on where I am, it's kind of tough. So when I'm in Atlanta, it's like, okay, I can do stuff that is kind of morningish. But if I'm going to a meeting somewhere, then essentially I have to do it either before the meetings or after the meetings, and that kind of complicates things a lot. Yeah, so I mean, we have four more minutes. So I'll just kind of sit here just in case somebody actually decides to call in at the last minute to ask the one last question or something. Okay, okay. So I guess nobody's asking anything anymore. So we'll just end these office hours. And again, I'll have to figure out my schedule when I get where I'm going, and I'll try to basically make an announcement on Monday or yeah, it has to be Monday because I'm kind of flying on Sunday. So I'll make an announcement on Monday then, like regarding what time of day on Tuesday is gonna be. There is a slight chance that it will have to be Wednesday just because Tuesday might be like particularly bad. But I'll because that's kind of the last office hours before the final exam. It has to be like Monday or Tuesday because we will begin the exam probably like Wednesday evening, Atlanta time. So I'll essentially find a time for Tuesday or Wednesday to have the office hours before the exam begins. Once the exam begins, basically, we will not have office hours anymore, just because on Tuesday morning I will, be grading the exam and trying to finish everything that needs to be finished and stuff like that. Because unlike the midterm, the final exam, we have only so much time to grade it before we need to turn in the grades, and also the projects and stuff like that need to be kind of you know graded on time. So it's kind of tight schedule for everything happening. But so this is going to be probably our last office hours next week, which is why we need to have them. So it's going to be again like Tuesday or Wednesday, at some time that is probably not going to be the time we have, but it might. I don't know. I mean, I'll have to figure it out. So thank you, and good luck.